Good morning. My name is Tolbert and this is my design of machine elements project. Today I'll walk you through the complete engineering process behind my Tamper seal bottle cap design. And I'll walk through it from concept to simulation, and then I'll go into failure analysis. I'll mainly focus on how we can engineer a seal that visually fails under realistic tampering conditions. So the goal of this project was to develop a tamper seal that clearly and irreversibly shows that a bottle has been opened. So I modeled the design based on real beverage cups, specifically selecting an aluminium alloy cup, which has lower, which in my design, the aluminum cup that I selected has a lower tampering ring, and it is connected by notched ligaments. Those notches concentrate the stress to control exactly where and how failure occurs. So this design was evaluated under torque loading to simulate how a user would attempt twisting off the cap. So for the design requirements, this project had to meet several key requirements. First, it needed to visually show when tampering had occurred. Second, it had to be non-reusable once broken. It has to stay broken, and it must fail under realistic torque, which is relatively between 15 and 70 pound-force inches. And that is it is similar to what users apply when opening normal water bottles or just commercial bottles like beer bottles or something like that. It is also another requirement was that the design had to be compatible with bottlenecks and failure, and it must cleanly show it must cleanly show failure at the ligaments to avoid misleading or partial breaks. And finally, another design requirement was that the material had to be cost effective and suitable for machining or molding. In terms of constraints, we could not rely on simple adhesives or shrink wraps when doing this project. So the failure had to be mechanical and built into the geometry, and that's what I did. I built the failure into the cap's geometry. The torque needed to stay below 60 pound-force inches to prevent excessive effort during opening, because if you have like a bottle cap that it is made from, let's say, stainless steel, and it's extremely difficult to open, then that would defeat the purpose, and it would defeat the purpose of the design constraints that we were given. Also, the cap shape has to be simple enough for manufacturing via injection molding or die casting. And lastly, the material behavior had to be brittle or semi-brittle to avoid plastic deformation that might allow resealing or deformation that might go unnoticed. This is the product I examined. So basically, I was examining an easy bottle that I bought from Chipotle, and here you can see what it looks like before the seal is broken. It is fully intact, and here after I have drunk it, you can see the seal. The seal has been broken, and it can't really be put back. I like this design because it is tamper evident, and once broken you can't really put it back, so you can't really glue it or anything. Or maybe you could weld it if you're really technical about it. You could weld it back, but the seal is tamper evident. It's a one-time use kind of seal, and this is the product that I examined. So for engineering considerations, very many engineering principles were considered when making this project. First, we had to use stress concentrations by designing notched ligaments. Second, I acknowledge that aluminum is a very strong material, but it makes it durable, but not ideal for tamper indication. That's why this whole project was interesting to me. Thirdly, the cap had to fail under torsional shear in my project, and my simulations will later on confirm that this is the dominant mode. Finally, manufacturability was also considered, and the geometry supports CNC milling or die casting, and there is no overly complex features in this geometry, so you can use it in different forms of manufacturing. It's highly manufacturable. My prototyping plan, for my prototyping plan, I used SolidWorks and I imported the model into ANSYS for analysis. I used ANSYS Workbench, and the key features for my prototype included a solid cap, a solid cylindrical cap with a textured outer surface for grip, and a thin tamper ring with breakaway ligaments. This is the SolidWorks geometry design that I made, and here you can see the patterned grip, which is unlike what's in CESO, but I included that to see what effects it has on the what stress effects it has on the bottle cap. Here you can also see the tampering on the bottom of the which is the bottom part of the bottle cap, and you can see little notches which are which are called the notched ligaments. With those little things between the top portion of the cap and the band and the bottom band, those I call the notched ligaments. So I imported the geometry into ANSYS and I assigned some aluminium properties. I assigned aluminium properties on the model, and I kept the generic alloy properties. So I didn't really change the actual properties in aluminium. I kept the generic aluminium alloy properties. And here you can clearly see the material selection that I kept for the aluminium alloy that I used. I selected aluminium 6061, which is good for its mechanical strength. It is cost effective, and it is relevant to my design because it also uses the same aluminium alloy for its designs. And here you can clearly see it has a density of about 2,700 kilograms per meter cubed, a Young's modulus of 70 GPa, a yield strength of 280 MPa, ultimate strength of 310 MPa, and this is all good because it shows that it can withstand a significant force. It can withstand some significant force, which is good for for the tamper seal design that I made. So for this project, I had to create boundary conditions, and this is my setup that I used in ANSYS. I basically added I applied a moment about the lower portion of the cap, so I didn't put the moment a little bit higher on the actual grooves. So I put it right next to the notched area because I am really trying to determine the stress that occurs there and see what happens when some torsional force is applied. So this is the moment, and that red band is where I applied the boundary condition for the moment that later on translates into the torsional shear. The other boundary condition I used was a fixed condition where I fixed the lower portion of the tamper seal. So the band itself, I fixed it on the bottle cap, because if you leave it unconstrained, then the bottle cap will just keep spinning and spinning and spinning. It will never really get the chance to break open. So that's why I fixed it as one of my boundary condition setups. So for failure mechanics, I made 3 simulations, and they were run at 1, 5, and 50 pound force inches. And this allowed me to analyze car performance under light, moderate, and excessive torque levels. I wanted to see what happens when I apply light torque, when I apply some moderate torque, or some excessive torque levels. And to me, light torque is about 1 pound force inch, and when you apply that, you get a max stress of 140 psi, which gives you a safety factor of about 28. When I applied the 5 pound force inch torque, it yielded about a 700 psi max max stress, and that was about a 56 safety factor. And I increased that tenfold, so I applied a 50 pound force inch torque, and that yielded about 7,000 psi, which gave me a safety factor of 5.6. So I used this data for failure mechanics to predict the torque at which the yielding, and I used this data to predict the torque at which the yielding and potential failure could occur. And in this slide, you can see shear stress analysis, which revealed about a 3,700 maximum psi in shear stress that is located mainly at the notches here, and you can visibly see that red portion that says max. That's where the maximum shear occurs, and it occurs at the notches, which is good for our simulation because it justifies the whole point of the project. In this slide, we observe the directional deformation, and it is seen it is seen as a z-axis deformation, where one portion of the cap moves up while the other stays in place, which essentially mimics it moving down. So the whole design, where the bottom portion of the cap is fixed, the deformation focuses on the strain on the ligaments, since when you try to twist it, when you try to apply the torque, it follows the grooves on the bottle cap. It follows the grooves on the bottle and the grooves inside the bottle cap. So it mimics this motion of going up while you're twisting it. But since the lower portion of the cap stays fixed, I used that to determine the directional deformation, and basically I found out that the cap experiences a maximum upward deformation of about 0.003 37 inches before it breaks. So zooming in, we see that the deformation is highest in the ligament zones, and this confirms that stress and strain localize in the thinned areas, which is exactly what we want in our Tamper seal design. And here, this is just a reiteration with a zoomed in portion, but it just shows the maximum deformation occurring at 0.003 inches, and that's where precisely the notch areas are. And this effectively further illustrates that, which amplifies this whole strain and stress evaluation. This overview shows the full cap's deformation under 50 pound force inch, which where the upper portion of the cap remains rigid while the tampering flexes significantly. And you can see, so you see the grooves of the cap are in red, and it shows that the most total deformation is there, but it slowly transitions into it slowly transitions into those thin ligaments, which later on makes the cap break or makes the tamper seal break. In this slide, we can see the equivalent von Mises strengths for the full von Mises stress for the full cap, and this von Mises analysis shows a max value of about 7,100 psi at the ligaments, and that is far below aluminium's yield strength, which I know it confirms that 50 pound force inches that we use to evaluate this design approaches plastic deformation, but it doesn't really exceed it. So it means if we go higher than 50 pound force inch, something like 60 or 70 pound force inch, we can surely get plastic deformation. So this is a second slide that shows the equivalent von Mises strength. But this slide is different from the first one because the first one showed the von Mises strength for the whole cap, and this one specifically shows the isolated von Mises stress on the lower portion of the cap, because that's really where the tamper seal is in those notched ligaments. And here we can see that we can see that the maximum stress is localized at about 5,000 psi, which is recorded on the inner side of the breakaway ring, and this is precisely helps us ensure that if the cap fails, it does so in the ring, not somewhere else we didn't expect. So I used the whole cap von Mises stress to show you where and how the cap fails, but I isolated the lower portion to even to precisely target and show us where the cap fails mostly. So in my prototype, in this prototype, plastic deformation, I found that plastic deformation begins at about 28 pound force inch, and it begins near 28 pound force, not exactly at that. And when I did some research, the realistic tamper torque should be between 15 and 70 pound force inches, and that is the 28 pound 4 inches torque is right above the strength of most 5 or 10-year-old children, who typically apply between 10 to 20 pound 4 inch when opening normal water bottles. So this makes the design child resistant because it's a little bit higher than what they can normally open. So it speaks volumes about the whole mindset the manufacturers used when making the product. So they made the product child resistant, even if the product is not alcoholic. It is just a probiotic drink. So maybe they put that into account, that probiotic drinks may be harmful to young kids. So when designing this project, my focus areas were stress concentration and fracture mechanics, and I was trying to determine where and how failure initiates. So this was one of my focus areas, and I found out that failure initiates at the notched ligaments due to the geometric stress that occurs there. My other focus areas were about the ductile versus brittle failure. I wanted to determine what materials and what mechanisms would lead to a predictable break. And I found that aluminium fails gradually, but a brittle plastic would fail quickly and visibly, which would be ideal for this use. But since my project is mainly focusing on aluminium, I focused on that, and I found that predictable failure is achieved by in aluminium products or aluminium bottle caps. Predictable failure is achieved by combining a brittle material like aluminium with a notched geometry that localizes the stress in those ligaments, which ensures a clean fracture, which ensures a clean fracture under expected tampering forces. So you can design it in a sort of way where it is very clear, whereby if, let's say, you made the same product with a different material like polystyrene, the fracture may not occur suddenly. It may elongate when you're twisting it. So that was the whole point of this project. My other focus areas were about shear, tension, and bending failure modes, and I wanted to find how my seal behaves under different forces. And I found out that shear dominates the whole failure mode, because when you apply torque, it generates a high shear stress in the ligaments that are connected to the tamper ring, and the max values were over 3,700 psi at 50 pound 4 inches, which is a lot of and tension and bending also occurred, but they were very minor stresses. They were just secondary. They weren't really primary to the whole objective of the design. My other focus areas were in fatigue and creep, and I was trying to determine whether my design can withstand prolonged stress without premature failure. And yes, I found out that the design can actually withstand prolonged stress without premature failure, since it was made from aluminium alloy. And this is really not a major concern for aluminium, because it does withstand prolonged stress. and we also know that the design is a tamper seal, so it is only designed for a single use term, so it does withstand prolonged stress, and there's not going to be any premature failure when you're using products that are made from aluminum alloy. In conclusion, um, this project simulated the tamper seal aluminum cap, and the tamper seal was analyzed under realistic torque showing plastic deformations, which begins near 28 pound-force inches, which is within the typical tampering ranges for this project. And to ensure predictable and visible breakage, I found that brittle materials with designed stress risers are recommended for a project like this, because if you use some sort of other material, it could fail to break effectively, which could be inefficient for the design. Yes, thank you. This was my project. Thank you for listening.